Well, hi everyone, and thank you for joining tonight's presentation with the Boston Beck. I'm Sarah Kravitz and I'm the chair. And before we get started, I want to go over a few housekeeping items. I posted a link in the chat. So if you want to receive AIA credits, please click the link and fill out the Google form and we'll follow up in the email with your certificate. Also, I welcome you to join our BSA Boston Beck LinkedIn group for upcoming updates on presentations and also our WAGNI and East Symposium that we're going to be putting together this fall. And I would like to introduce our speaker, Wei Lam. He is the director of RDH, or the principal at RDH in the Boston office. He also has multiple years in experience with building envelope consulting, especially with design, specifications, engineering, and troubleshooting. He's also presented previously at the WAGNI and East Symposium a couple years ago, and he's a personal favorite presenter of mine. So we are very lucky and appreciative to have you, Wei. Thank you for being with us and giving us your time today.
Sarah, thanks for the kind introduction. I hope I can meet the standard today. Hello, everyone. Good afternoon. I am calling in from Austin, Texas today. I'm here at the Humid Climate Conference, which I don't know if any of you've had the pleasure of attending, but it's a great little conference. This is my first year. I'm here with a couple colleagues. My colleague John Straub was presenting earlier today, or he was the keynote actually. Great little presentation that's hosted by, or conference that's hosted by Passive House Austin. So just a little plug there, and if you get a chance to get down to Austin sometime and attend the conference, great little conference. Thanks for joining again. Today we are going to be, let me advance the slides here. Whoops, just make sure you're in the right place here. Slope glazing and skylights 101. A fairly high level review of slope glazing and skylights with a few examples, illustrative examples to sort of make the point. Just quickly, a little bit about RDH. We're about 300 people across US and Canada with 9 offices. We've got about 6 million plus square feet of high performance project experience. Our focus is on building science and the building enclosures. Certainly, if you want to learn more, you can go to our website, rdh.com. The types of services that we provide, building enclosure consulting is sort of at the core of our offering. Energy and sustainability, facade consulting and structural engineering. So developing design assist facade packages for custom unitized curtain wall. Maintenance and capital planning for condominiums, universities, other institutions, and healthcare. Material science and research, we have a lab in Waterloo. Investigation and litigation report for our attorney clients, and building enclosure commissioning to round it all out. So, Sarah, you can hear me? I just want to make sure we got a sound check. We all good?
Yep, I can hear you.
Great. So the topics covered today, sort of a couple questions here, or maybe a couple statements. What do we mean by slope glazing and skylights? A review of the critical barriers for both slope glazing and skylights, and then a few illustrative case studies. So what do we mean by slope glazing or skylights? Well, you know, if we take a look at the code, AMA and ASHRAE, we find that they all have something to say about slope glazing and skylights. So we're going to take a little run through what those various documents, how they define slope glazing, and maybe what some of the differences are, so that we sort of set the table for a further discussion on barriers. So the North American Fenestration Standard, NAFS, presents us with several skylight product types. What's outside, you know, slope glazing systems are outside of that, within the scope of NAFS, we have unit skylights, roof windows, and tubular daylighting devices. Outside of the scope of NAFS, or, you know, as I call it, AMA 101, we have slope glazing systems. And what you'll see here is, you know, not unit glazing, but a system that employs purlins and girts. So this is some language directly out of the NAF standard. And you'll see that red underline there. It says fenestration products not intended to be tested to the standard include. And then if you look a little further down to item D there, you'll see slope glazing. Within IBC, section 2405, that section is titled slope glazing and skylights. Glass, it defines those products, including glass and other materials installed at slope more than 15 degrees from vertical. It lists and summarizes some allowable glazing materials, including laminated glass, heat strengthened and fully tempered. It also discusses some requirements for screening for monolithic glass. I can say with good certainty, I've not seen too many screened skylights in my time, but perhaps that's something we could talk about further as we get into the presentation a little bit more. I would welcome you to sort of interrupt me, and you can put some questions in the chat if you want, and Sarah can sort of interrupt me. But hopefully we can have some discussion here through the course of the presentation. Oops. 2405 goes on to talk about framing in type 1 and 2 construction. That's non-combustible material. The framing's got to be non-combustible materials. Less than 45 degrees, there's a statement in section 2405 that says at less than 45 degrees, if that slope glazing is at less than 45 degrees from horizontal, it requires a 4-inch curb. There is an exception for that, and I've never really understood this exception. Maybe somebody can explain it to me. You can install without a curb at slopes of 3 and 12 or greater for group R3 projects. Unit skylights and tubular devices are further defined, and they talk about those products being labeled through AMA 101.
Before we move on, we do have a question from Richard asking, what is a screened skylight?
So the code describes screening. So underneath monolithic, under some situations where you may not have heat strengthened glass, that you have a screen that can retain, is designed to structurally retain glass breakage below the skylight. So I have never seen that. Perhaps I'm misinterpreting that, but I think most of the time when folks are considering the design of slope glazing, they don't want something visually interfering. So I can't think of an application where I've seen that before. I've certainly seen safety appliances or materials applied on the exterior side, but not on the interior side. Was that Richard Keller?
Yeah.
Yeah. All right, moving on. Maximum skylight, maximum. So the IEC, the International Energy Conservation Code, goes on to talk about maximum skylight areas. So these are unit skylight areas. There's some information in there about 3% of gross roof area. And if you apply certain daylight responsive controls, you can up that skylight area to approximately, to a maximum of 5%. ASHRAE 90.1, in this case, I looked more closely at 2013, defines skylight as a glazed surface with a slope less than 60 degrees from horizontal, so slightly different from the other codes or documents that we've reviewed or discussed already. All other fenestration is considered vertical. There's some very specific requirements within ASHRAE 90.1 with regard to air leakage. So 0.3 CFM per square foot at approximately 1.6 PSF, and slightly higher leakage rate, prescriptive leakage rate at the higher 6.24 PSF. ASHRAE 90.1 also requires skylight curb insulation to match the roof insulation or R5, whichever is less. So in retrofits, which we'll talk about, or repairs, you're often required for substantial work to improve the curb or insulate the curbs as part of skylight replacement. So just to summarize then, Skylights in ASHRAE 90.1, Skylight, is a skylight is a skylight with a curb, right? It's curb mounted. It's a unit, the unit skylight, right? Something like a Velux skylight. That's far different than a skylight without a curb. So in ASHRAE 90.1, the interpretation is that that is a slope glazing system similar to what you see there in the image. So just a quick takeaway here, we need to be clear about the distinctions the code makes between the two categories of overhead glazing products. Unit skylights, these are factory glazed units. They might include operable roof windows or the tubular devices, daylighting devices, and they may be curb or deck mounted units with integral curb. So again, what's commercially available and through retail outlets like a Velux skylight. Slope glazing is typically field glazed and contains multiple lights of glass or plastic glazing. And we'll talk about the framing in a little bit here. So when we're thinking about skylights in design, NAFS distinguishes, sort of summing up the sort of discussion to the point up to this point here. NAFS distinguishes between unit skylights, roof windows, and tubular devices, but excludes slope glazing from its scope. 90.1 distinguishes between curb-mounted skylights and sloped curtain wall skylights with different U values for each. I haven't covered that today, but certainly if you dig into 90.1, you'll find that there are prescriptive prescriptive requirements for skylights with respect to their size and construction. The code distinguishes between unit skylights and other glaze system, which includes slope glazing. So there's a lot of information. Let me just stop there and say that there's a lot of information in those three documents. I won't say that they're inconsistent with one another, but it's presented in different ways. So as you engage in a project, a skylight replacement project or a skylight specification project, understanding what each of those requirements, each of those documents requires is sort of fundamental. Also fundamental is understanding the critical barriers of slope glazing and skylights. This is not much different than walls. We're going to talk about the same types of barriers. The materials and components that perform the function within a building enclosure, those are the critical barriers. There's the water shedding surface. This is the first surface that the rain meets. Just think of it that way. There's the water resistive barrier. This is the barrier that may shed, that may be concealed and will shed the water. And it should be, this should be in a continuous plane so that the water is directed back out of the system. There's the air barrier, preventing the passage, undesired passage or movement of air across the system. And then of course, very similarly, the vapor retarder. You'll see I borrowed this from some of my Canadian folks, some of my Canadian colleagues. I should have changed it to vapor, spelled the correct way, I guess. When designing or installing products like skylights, you need to identify the critical barriers in adjacent assemblies, right? Making the connections to those assemblies is critical. This is the same as vertical fenestration or any other interruption or transition of materials in a wall or window system. The continuity we already talked about here. Continuity is critical at penetrations, at joints, and within the assembly. So within the joinery of skylights. If we look at a typical unit skylight, there are we'll cover a couple of the barriers here. The water shedding surface is this surface, this bubble surface here. Over this bubble skylight, a bubble unit skylight. You see it in the dash blue there. The water resistive barrier is located in a very similar plane, but not quite exactly the same. And so this is the plane that controls water, that's controlling water, that manages past the water shedding surface. Oh, looks like we missed the air barrier here. We'll get it in there, just out of order here. Oops, we'll go back there. The vapor retarder in this case is in line with the air barrier. Looks like I missed a line here, but it ties in from the curb to the unit skylight body itself. In slope glazing, very similarly, we have a typical sort of shed section here. The water shedding surface is outlined in the blue. Again, the water resistive barrier follows a similar line and collects water in the purlins, as you see there in that little, showing a little water drop there, if you will. But continues down in a similar fashion to the lower sill purlin, where water will collect and then be directed to the vertical rafters. So now if you focus on the section of the rafter there, you can see the line of the water resistive barrier. It is extends down on top of the mullion, and the water is managed there between the glass. And it's like the lines are out of the animation's a little out of order here. We'll just get through it here. The air barrier will follow the inside plane of glass and the interior plane defined by the mullions, or rather the rafters and the purlins. And the vapor retarder following a very similar line. So just to cover a little bit of slope framing terminology, I've already used it a little bit. The rafters are the vertical components, the vertical mullions that span the opening structurally and drain infiltrating water to the exterior. The purlins span between rafters and drain the infiltrating water to the rafters. Purlins and rafters typically have different cross-section profiles, with the rafters generally having the deeper section, and the structural purlins having a shallower section. Slope glazing system drainage. So this is an important piece of our discussion here. I'm just going to open up all of the slides here. I'll proceed this way. Slope glazing different how they manage water. In an open gutter system, the water is managed and drained below the glass line, and so sort of outside of the glazing pocket. This kind of system results in a sort of direct connection of the interior space with the exterior space, because the water's got to get out through weeps. And so inherently, as this water travels down the rafter, it needs to find an exit at the base of that rafter that connects to the outside. Inherently, because these are sort of open gutter systems, and what we mean by that is open to the interior, they lend themselves to slightly higher risk when it comes to managing water, right? If you have some obstruction, if there's some overflow, if there's more water than than anticipated, it's can directly access the interior. In a closed gutter system, these systems provide drainage within the glazing pockets, if you will, right? So in the purlins, this is within the sort of contained between the purlin and the glass line. So we consider this a closed gutter system. That water is not exposed or have any pathway to the interior. It's directed to channels within the rafter that direct it down and out of the system. And if adequately, if properly detailed, that water should never, those spaces, those volumes should never see, quote unquote, see the inside. And this is a very effective way of draining and managing both water and condensation in slope glazing systems. So closed gutter systems allow drainage without penetrating air barrier between the skylight and sill. I already talked about that. Here's a very typical arrangement for that type of system. And the detailing, how you detail various components at the sill, this becomes a sort of critical component to the performance of these types of systems. The other thing is, and we'll see in some examples, is that this really allows you to provide insulation thermal insulation at the sill in a sort of well-protected way. The detail here, going through a little bit of a sequence, showing the self-adhered membrane that can be detailed so that the water is then directed out of the system. So just a couple quick notes on structural considerations and loads. I just figured we talk about this very quickly. Dead loads, you need to consider glazing, purlins, rafters, and the miscellaneous components related to the system. Wind uplift, typically higher than wall loads, and needs to be considered sort of carefully. In many of these larger, sort of larger projects that I've worked on in any case, we've relied, we generally see a wind tunnel study that we'll look at carefully. So some of the larger, some of the larger applications, certainly not for unit skylights. Drifting, snow drifting needs to be considered. There are two sort of types of drifting, leeward and windward drifting, and those should be considered. Of course, structural should consider that and should have that covered in their analysis. And that would certainly fall on a facade designer. So we're frequently looking at that kind of load to better understand and apply the code. ASC 7 as required. Live loads, consider construction workers, uniform load of 20 PSF and concentrated loads of 300 pounds, up to 300 pounds. Just one other thing very quickly, pinning the top and bottom of the mullion, or rather of the rafter versus a pin and roller connection. Some of the advantages, I'll just speak to the pin and roller. You got lower lateral reactions at the connections, so that you can have a more slender rafter. Rather a larger rafter connection and heavy splice connection. So the pinned connection will allow you to have a smaller section, but larger reactions at the connection. So a larger beefier sort of connection anchor point there. All right. Any questions, Sarah, up to this point?
No questions so far, but I actually do have a question. Can you go back to your previous slide?
Yep.
So the roller, you're saying that it can have like smaller, I guess, like mullion structural support, but or is that, am I getting that
No,
larger?
I misspoke, Sarah. I misspoke.
Okay, gotcha.
So with the pin and roller connection, you're gonna have a larger rafter section.
Okay, thank you.
Yeah. All right, so a few case studies, actually two specific case studies, and then just a couple other mentions of projects that we're working on right now where I wanted to point out some rather, I guess, softer points, not so much technical, but really considering what we're facing in light of repairing and updating our existing buildings. So this first project, I can't tell you what project it is, but I can talk about it. It's a Seaport Life Science project. On the left here, you see a plan view in blue. You see a highlighted sort of linear section of Skylight that abuts the adjacent building to the left. So in that center view, that's a section cut. You see the Skylight. Let's see if I can get there. Sarah, can you see my arrow, my pointer?
Yes, I can.
Okay, so this is the Skylight in section here. There's a little balcony area here, but this is the adjacent property here, and then a axon sort of showing that same condition there. So the design intent, this is the architectural drawing, the original drawing that we had some opportunity to review. This was the original design intent, providing some continuity of insulation at this double glazed piece of glass. You'll see that it evolved somewhat from this as it went into shop drawings and as the contractor started to look at it. But the intent really is to provide some daylight and then a rather finished condition here incorporating the glass and the surrounding flashings and finishes. So the contractor's first attempt, this was one of the first versions of the shop drawings here, sort of literal interpretation maybe of what the architect had shown, but there were some comments here, in particular at the sill here, looking at what was happening with the insulation and whether the insulation could come closer to this transition line. And also how drainage, there were questions about how the drainage was being provided. You'll see here a enlarged detail of that same condition, and some markups from the consultant. It was not us in this case. We were providing some, I guess, auxiliary comments from the curtain wall consultant on this particular project. But you could see the alignment of the insulation. I agree with this. You know, the insulation needs to come closer to the frame as opposed to being sort of all the way out here and quite far from the mullion. And then a few other comments here would be, you know, what's the drainage pathway here? What is the drainage pathway for water exiting that vertical rafter? And then this note up here, this was a question about dew point, but you know, the condensation is going to occur on any of these surfaces, right? I mean, it's not going to occur within the insulation. These are non-permeable materials. We don't care if insulation, you know, if condensation occurs necessarily out in this zone, so long as it's managed. Similarly, enlarged section detail of the head. And sorry, I'm looking up because I've got a large screen in front of me and a small screen closer to me, but I can't quite see that. So we'll go from here. Again, you know, less comments from the consultant in this case. Not so much concerned with water management here, but I can tell you one of our concerns was the connection to the existing building. And so we couldn't touch the existing building, but we did know that this space, if I go back here for a moment, just to remind you what this looks like, there's a very narrow space here, and we did want to close, you know, we did want to find a way to close this off effectively if possible. And that turned out not to be possible. This owner really did not want anything attached or even come any closer than that to their building. And then a couple end rafter and rafter detail conditions. This was the original concept here. You can see that there's a piece of metal or flashing wrapping the edge of the IGU here. I think this is, you know, this is somewhat concerning, obviously, for laminated glass. As water gets trapped in these areas and water, you know, the potential for water sitting against the lamination could be fairly detrimental. And cause delamination of the inner layer. There were a few comments here. In particular, there was a suggestion to provide some drainage, which I think we agree with wholeheartedly. The glass buildup also changed a bit. You can see that here. But the consultant was really concerned about providing some drainage here, which we did agree with. So ultimately, the record shops, you can see that things changed fairly significantly from the first round of details. This included pushing back the sill quite a bit, adding some insulation and anchorage, but also getting the drainage that rafter extended well beyond the last sort of purlin here in order to drain those conditions. And you know, these details of the glazing ends and rafters also updated to reflect the changes. So you can't quite see it here, but there's a weep called out in this note here. And then really, well, this one was supposed to be trimmed. Now you got to see what project it is. Sarah, this is one of Consigli's. This is actually a really nice detail, you know, really nice piece of the the set and a required, required piece. What I like in particular, not so much the splicing detail, this is fairly straightforward, but this really provides information about how this system manages water within. So from the purlins, and in this case, there were no intermediates. This actually didn't apply to the projects, to the specific project conditions. But in this case, it really sort of illustrates, even in a rudimentary way, how water is managed from the purlins to the rafters. So a couple photos from construction. I took these as we were looking at a lot of the roofing and waterproofing in this case, but also the interface condition. And what you'll notice here is that, inherent to a lot of these, there was some buildup here that was unanticipated. There's some blocking here over the steel, a little bit of a miss. And, I don't know that it had much impact on ultimately how the system was flashed. But that's how it goes. And then a shot at the end here. I don't know if you caught the fact that the ends of this are glazed, right? So there's some glass here supported below that comes up and meets that. But there's a fairly large, if you can see it here, there's a fairly large joint between the glass, and that that was anticipated to look maybe plus or minus, look like a 3/4 inch. So there was geometrically, this is a pretty complex assembly. And then I think there were comments around the insulation, but then you think about these end conditions which were not anticipated. And I think this is why we took this particular photo, was to understand how the roofing was coming in, and also how this end condition was being resolved. If you can see the arrow my arrow right here, you can see the end of this mullion right here. So you have the raceway. You can see the race. This is the raceway here. You can make out the raceway. I think right about here. So this end condition needed to be capped off in order to provide some continuity to the various barrier control layers. Let's see. How are we doing on time? All right. I'm going to go on and talk a little bit about a project that really came out of some of my colleagues in British Columbia. I think this project is a nice example of what can be done practically in existing conditions, not ground up construction. The Clink building is a classroom building on the University of British Columbia campus. I think it's a 1950s, I believe, was the original construction. Oops. Plan view here, a couple sort of pyramid skylights, skylights, and then some of these monitors that are copper clad, seen better days, clearly. This is existing slope glazing. The skylight replacement was part of an overall roof replacement project. You can see here the skylights had been sort of over the years had been abandoned and blocked up. They were no longer being used. I think they were very leaky and creating a lot of problems. So they somehow, this was their solution. Somehow I didn't get the details on this. They basically abandoned the glazed units. So this is what it looks like. Looks like new. And I'm going to talk a little bit about what they did. But they did reuse the existing framing and converted the system to a sort of more modern system. This is the existing pyramid skylights, and you can see the curbs not insulated here. Curb very low as well. And here, the updated pyramid skylight looking much better. So the Clink purlin rafter drainage as a closed gutter drainage method was desired, right? That's where we wanted to get to for critical barrier continuity within the system and in the adjacent assemblies. The original design was an open gutter. So the question was how do we convert this in a practical way? So this is sort of showing where the water is managed, and in this particular system, this is open drainage, and you can see the drainage is occurring here, and you're not going to. It's more or less exposed to the inside. The modified, by modifying the system, it meant extending the purlin so that it was cut in or coped into the vertical rafter. And now you're able to manage water in that sort of glazing, what I call a glazing pocket zone, or in that channel, where it now becomes a closed gutter drainage system. And that would require some sealant here, effective sealant between the purlin and the rafter. So this is just a section view here of the typical construction, showing the new roof insulation and insulation over the top of that monitor, I guess, sloped monitor condition. I don't actually know if there's a proper term for this. I'm sure there's an architect in the room that knows. But providing thermal continuity, thermal insulation continuity at the sill and at the head, wrapping those concrete members and tying that into the new skylight assembly. So just to look at the barriers again, the water shedding surface is that primary surface, or that most exterior surface. The water resistive barrier here a bit buried, below that, where water could be managed ultimately, but the last line of defense for water. The air barrier in this case, not coming, there we go. Also in line, in the same plane with that water resistive barrier. So here's some examples of the finished work, or the work in progress rather. Used a foil-faced AVB in this case for that water resistive barrier and air barrier. A few more details here, sort of showing the construction and the application of the thermal insulation in the head conditions. And then switching to the pyramid slope glazing sill, again, adding some height to that curb, getting it up off the roof, and then looking at the water resistive barrier here, again, sort of buried down at the shoulder of that purlin, or rather at the base of that rafter. And the vapor retarder and air barrier sort of following in line and tying in with the temporary roof / vapor retarder from the roof system. So the closed gutter system allows drainage without penetrating the air barrier between the sill and skylight. And so we saw this drawing earlier, just to refresh. This water, any water coming in to the sill, rather coming into the purlins here, directed into that channel of the vertical rafter, and then outside of the system. So in real life, if it were, as you will, this is the system. You'll see that the rafter, the rafter extends quite significantly past that lower purlin, and then this will be closed off with flashings and insulation, exterior insulation, a little Z-girt and cleat here to hold on the flashing on there.
We have one question from Rick. Why was foil-faced AVB used?
I don't know that, Rick. I think this is C-Plast Viral, and so it may have been done for fire. It may have been done for fire, but I actually don't know why they use this particular membrane. But I'll find out and let you know, Rick. Yep. Oh, sorry. This is the pyramid. This is the pyramid lights. So very similar, sort of coming up. You're insulating that. You're able to insulate that sill, and then the slope glazing. Cutting to the slope glazing sill. This was adding insulation to that. Adding insulation to that condition while maintaining continuity of the various barriers, and as you'll see, drainage for the system on the inboard side of the mineral wool insulation that was applied there, right? So closing this all off, but allowing those systems to drain out onto the roof basically out onto the roof surface. Remember, the water shedding surface is not actually a membrane or anything. It's simply shedding, the various components and materials shedding water. So in this case, the IGU down to the flashing, and ultimately onto the roof. So in this case, air barrier and vapor retarder are located co-located with the water resistive barrier. Oops. And so here is the slope glazing sill. This was the sheet metal support membrane that gets installed. Oops. Well, looks like I don't quite have it, but this was intended to close off the sections here and make it easier to apply these this transition membrane onto the roofing. So a few more photos here of that condition. You see the pressure plate. You see the pressure plate, or rather, let's see this closure plate here that's supporting. It's closing off this condition and providing anchorage for that cleat. You see that the membrane's sort of wrapped around. So fairly detailed cutting of the mineral wool, but it's all going to get sort of encapsulated. So this was at the jam. These are at the jam conditions. Again, here's this concrete, the concrete substrate. All the lines are already there. So whoops. So this is a fairly straightforward detail. Again, the water resistive barrier is tying into the shoulder of the mullion, and so because you don't have a sort of really flat surface here like you might in typical, in a curtain wall extrusion, you're generally tying it in up above with a little bit of a spacer, and that's providing the continuity that you need. Of course, all of these conditions, they terminate to the underside of the concrete. This is at the head condition where it's being transitioned. So you've got a little bit of detailing and consideration what you're going to do here. In this case, you can see that these surfaces were primed and there was additional AVB installed in those conditions. A few more photos really of just the complexity here of this kind of, on this kind of project. You can see that, encapsulating the concrete structure here took quite a bit of sort of geometric gymnastics in terms of continuity of flashings and the insulation, attaching the insulation. Maybe not the prettiest looking thing here, but when it was all buttoned up, it looked fantastic, and I think it significantly improved the performance and utility of these skylights and long-term maintenance, a much needed deferred maintenance on this project. So the scope was to renew the roof and replace the skylights. They had to bring the insulation on the curbs up to ASHRAE 90.1 levels, prescriptive requirements. The slope glazing system, this was a particular system, Spectrum Skyworks tubular rafter pressure plate system was used. So this was a design, something that they went out and sort of delegated design, understood what the intent was, conveyed that to the contractor, and I think a fairly decent system and components were identified to make that repair. All right. Any questions up to that point? I got a couple more slides here, and then I think I'm close to being done. Sarah, anything?
Sorry, I had a barking dog in the background.
Oh, it's
but no, so we don't have any questions,
okay.
But I think I'll save one to the very end about the project that you just went over.
Okay. We are currently involved in a couple projects, and I just wanted to, sort of put them up on the screen here. The complexity here is really access. This is 640 Memorial Drive. We're looking at this for Alexandria Real Estate, doing a condition assessment. This is the old Ford Motor plant just off Memorial Drive. Great old building, seen a few renovations over the years, looking to do some capital improvements right now. But one of the interesting things is that there's this, sort of steel, remaining steel structure that was original to the building. But they built a beautiful atrium slope glazing in one of the last renovations of this building. But I put these two pictures up here because the glass lights are starting to fail. There's a lot of deferred maintenance in terms of sealants in the slope glazing. And this giant steel cage prevents any sort of direct access, right? Very difficult to sort of get in there and do anything with a lift. And so, we're still trying to understand and figure out how we're going to access some of these conditions in a practical and sort of efficient way. And so important to think about, these systems require maintenance. They require cleaning. How do you get there? How do you take the glass out? This is not unbelievably, these are exterior, well, not unbelievably, quite logically, these are exterior glazed units. And so trying to get in there with a hoist or any other kind of equipment, really a huge challenge. The other project that we're looking at right now is the Ruggles MBTA station. This is with through some work we're doing with AECOM. If you know, Ruggles has this large barrel vaulted copper roof that extends the full length of the platform or sort of passenger area. And then this slope glazing that's quite cut up with vertical rafters and a lot of purlins. The current drainage strategy is to just any water coming off this barrel roof basically drains down onto this transition point here, and then flows out onto this low slope roof across the slope glazing. This is creating a lot of problems. There's a lot of leakage. The space below this is not occupied, so and it's really just it's a T-stop. But they're finally getting around to fixing this, and the idea here, at least for this area here, the slope glazing area, is probably to incorporate a system with polycarbonate panels, eliminate actually all of the purlins here, and get a polycarbonate panel that will run continuously and provide a better flow for drainage transfer across onto this roof. There has been some consideration of installing a gutter at the base of this barrel vaulted roof, between the barrel vaulted roof and the slope glazing. We've looked at that up, quite a few times now, and our position is, who's going to get up here and maintain that gutter? That gutter is going to get full, full of junk. It's going to be difficult to maintain. We think that this has worked quite well. This drainage strategy off the barrel roof has worked quite well for a long time. There's just a lot of deferred maintenance that needs to occur. And here you can see sort of a close-up of what that condition looks like right now. There's some voids. There are some voids in various flashings here, but for the most part, this water just cascades down across this system. So just a few concluding thoughts, all out of order here. Pay attention to skylight terminology. The code, ASHRAE and NAFs all sort of have different requirements and define those systems somewhat differently. So encourage you to dive into those. There's a lot of information there, and I frankly, I think, even for me, looking at it, it seems like there's sometimes some inconsistency between those. They're not quite coordinated as well as you might hope. And think of in terms of critical barriers, right? This is sort of part and parcel to everything, at least that I do, is to think about heat, air, and moisture. How are we controlling those elements and loads across these systems? And the last point here, some of these materials, as we saw, perform multiple functions for in terms of continuity of those barriers, and should be considered carefully as you're detailing those. All right, Sarah, I am done. That's the presentation, and glad to entertain questions.
Well, thank you. Really appreciate that. And one question that I had for you was back on the 105 West, like First Street project. Like, what did you do at the very end? You showed a picture of like a section detailed like where it terminates, but how did you like stop that drainage? And I guess like when you wait, I think you passed it. One more.
That
yes,
one.
that one. So like that purlin that you were talking about, like how did you end up closing all of this off?
Sarah, that's a great question. I actually don't have the answer to that, and in part we were looking at roofing and waterproofing. So I think this question went back to front. We were looking at all the roofing and waterproofing here, and the transition into the system, but how that would terminate, whether that was this wasn't going to be roofing and waterproofing. So I'm not trying to pass the buck, but I'm not really sure how this got finished. But I know this is why the photo was taken. So maybe you and I need to go back and revisit what actually happened there.
All right, I'll dig it up.
There's there's only two of them on the whole project, right? So there's this one and there's the one at the other end.
Well, it seems like a really interesting project nonetheless.
It certainly was, and we're just finishing up. I will point out, that through COVID, I mean, this project was delivered primarily through COVID, and there were a lot of delays. And it is really good to see this particular consigli project starting to wrap up now. It's a cool little building.
And on the other side, was there like a gutter, like at the base between that little gap between the next to the adjacent building?
No, this was no, this is just open. It just rains, and I don't know. We were joking that dead seagulls are going to fall down there, and all sorts of. So this is it's fairly contentious with that landowner to that on that side. In terms of touching the building, there were a lot, and maybe a point for another discussion down at the base of this, closing that off to prevent sort of unwanted access by people or animals or anything, was fairly challenging to think about, given that the working space was less than 24 inches wide, right? So getting in there, we came up with some very clever ideas about how to use eaves and inflatable bladders to basically stick the eaves to the wall where we couldn't get into it. And at the end of the day, I think that it was really just sort of left exposed until we can find a better sort of well, actually that's not true. It was not left exposed. There was insulation installed, but I think the insulation didn't require as much complexity as we had anticipated. I think they found a really small person to get in there and actually get it done. Yeah.
Yeah, talk about tricky detailing.
Yeah, exactly right.
You have to be ABBA certified and under 4 feet.
That's right. Yeah, exactly.
Well, thank you so much. I found it very informative. And also for those who missed the, I guess, opening remarks, in the chat, I'm going to post a link. So if you would like to receive AIA credits, please fill out the Google form, and then we can follow up with an email sending your certificate. Also, additionally, we welcome you to join and join and follow our LinkedIn group. It's called BSA Boston Beck for all of our upcoming events. And another thing is also on our website within a couple of weeks. This presentation has been recorded. So if you would like to share it or refer to it at a later time, please do so. It's also on our website as well. Let's see, does anyone have any ending questions? Well, thank you, A. We appreciate your time, especially of your busy day. We can go back to your conference.
I got another hour left here. Thanks, Sarah. Thanks, everyone.
Thank you.
Good presentation.
Thanks, everyone. Have a good evening.
You too. Bye-bye.